how do we know how old the Sun is? Our existence depends on the Sun. When clouds get in the way, or we rotate away from it on the Earth and have our nighttime, it's there, radiating light in all directions and sustaining life on Earth. However, you don't get something for nothing. The Sun is shining bright, but how long will it last? How long has it been there for? In astronomy, most research is done with telescopes, but this isn't always the case. Over 40 tons of material falls on the Earth every day, and sometimes the pieces are large enough to survive their fiery journey through the atmosphere and reach the ground. These space rocks, called meteorites, contain the information we need to find out the age of our solar system. If we wanted to find out the age of an ancient Egyptian mummy, we could use a technique called carbon dating. However, meteorites don't contain life as far as we know. But we could use another method to determine their age: rubidium dating. We can study the decay of the element rubidium and find out their age. But how does this help us find the age of the Sun? Well, the Earth, the planets, comets and moons all formed at the same time as the Sun. So, space rock rubidium tells us the Sun is 4.5 billion years old. But what does this number mean? Is our Sun young? Is it middle-aged? Or is it collecting its pension? To answer this, we need to delve deeper into the Sun itself. At the heart of our star, the temperature hits an unimaginably hot 15 million degrees Celsius. Here, bits of hydrogen are fused together, producing helium and energy. In these reactions, a small amount of the mass is converted into energy. The conversion is outlined in Einstein's famous equation, E equals mc squared. Here, E is the energy released, m is the missing mass that is changed into energy, and c is the speed of light. The Sun does not have a limitless supply of fuel. It will eventually run out of hydrogen, but when? Well, to work this out, first of all, we need to weigh the Sun. Set aside those cosmic weighing scales. We need to bring in two astronomical heavyweights, Johannes Kepler and Isaac Newton. Kepler studied the motions of the planets and didn't quite understand why they stayed in orbit around the Sun, until Newton came along 80 years later and formulated gravity. Using Kepler's laws and Newton's laws of gravitation, the mass of the Sun can be calculated as being equivalent to 4,000 trillion hippos. So, fast forward 200 years and we have E equals mc squared and the mass of the Sun. Now we have the tools to work out how much energy is thrown out from the Sun. We have yet to obtain detailed blueprints for the inside of a star, but star models assume that 10% of the Sun is hot enough to undergo nuclear fusion. In each reaction, 7/10 of the original hydrogen mass is converted into energy. That energy eventually spreads out from a star into space like a balloon, getting thinner and thinner. We don't feel the full brunt of this radiation, as we are 150 million kilometers away. We can measure the amount of energy that falls on the Earth, and if we know the distance to the Sun, we can work out how much energy leaves the Sun in the first place. Finally, if we know how much fuel our star has, we can find out how long it will last. It turns out the Sun is a middle-aged star, as it has enough fuel to keep going for another 5 billion years, after which the star we know and love will start to look very different. Hopefully by then, we will have colonized another planet, and future humans from Earth 2.0 can witness the next stage in the life cycle of our Sun.